Hello and welcome back to Machine Learning. I'm Jovita Christie, and in this video, we are going to talk about the convolutional neural networks. So let's begin. First, let's talk about what is a CNN. CNN stands for a convolutional neural network, and CNNs are nothing but ordinary neural networks, but they assume that the inputs are all images. So instead of assuming that inputs are anything else like numbers, here in CNNs, all inputs are images, and they are used to analyze and classify images, cluster images by similarity, and perform object recognition within a frame. So if you wanted to detect a person from an image, you could do that. If you wanted to classify images as images of cats or dogs or some other animals, you could do that with this. If you wanted to do clustering of images, that means group similar images together. For example, photographs taken in winter and photographs taken in summer. If you wanted to group them together, you could do all that with a CNN. Now, for example, you can use a CNN to identify faces, individuals, even street signs, and tumors, and platypuses. Platypuses are a type of animal, and many other aspects of visual data. And convolutional neural networks are also known as convnets, or they are also called CNNs. Now let's talk about how exactly these CNNs or convolutional networks learn. So images we know are made up of pixels, and each pixel is represented by a number between 0 and 255. So it depends on how many pixels are there in your image. That many pixels are required to represent the image, and for every pixel, there is a value from 0 to 0 and 255. Therefore, each image has a digital representation, and that's how computers can work with images, because computers cannot just process images just like that. They have to be converted into a digital representation. Once they're converted, there are four major operations in CNN. Actually, five major operations, but the last one is not an operation. That's why it's just four. So if you want to, just do classification of images, or you want to detect an image, detect an object within an image, then there are four major things that you need to do in a CNN. And those are: number one, convolution; number two, activation map; number three, max pooling; number four, flattening. And after you've done all this, you will have a fully connected layer, which will form a part of your CNN. So let's see all these steps one by one in detail. Let's talk about convolution. So convolution operation works on two signals in 1D and two images in 2D. Okay, so two signals in 1D, and 1D is one dimension, and two images in 2D, which are two dimensions, because images are represented in the form of a matrix. The main purpose of a convolutional layer is to detect features or visual features in images like edges, lines, color drops, etc. Okay, so if you had an image where everything was white except there was one small triangle in between, then this convolutional layer would be able to detect it because of the edges and lines that the triangle has. So it's a very interesting property, because once it has learned a characteristic at a specific point on the image, it can recognize that characteristic later in any part of that image. So CNNs also make use of filters. Filters are also known as kernels or feature detectors, which detect features, which we just saw, edges and lines and all that. And a filter is just a matrix of values called weights that are trained to detect specific features. So if you wanted to search for edges, then you could do that with a filter. If you wanted to search for something else, like maybe a color drop, Like, there's a black color, there's a whole region of black color, which then automatically just converts into some other color. So the filter moves over each point or each part of the image to check if the feature it is meant to detect is present or not. Okay. And to provide a value representing how confident it is that a specific feature is present, the filter carries out a convolution operation, which is an element-wise product and sum between two matrices. Okay. You'll understand this better with an example, which we will see in a minute. So basically, it's about taking two matrices and trying to add them or multiply them to get some answer or to get some insight into whether or not there is an object to be detected or classified. And whenever a feature is present in part of an image, then the convolution operation between the filter and that part of the image results in a real number with a very high value. Okay, so if you have two images which are similar, then the matrices that you form with both the images, if you multiply them, you'll get a really high real number, which would show that both images are more or less similar. If the feature is not present, then multiplication or addition of the matrices results in a lower number. So here is an example. You can see this is a plus sign. So this is my original image. If I have to show this image with a matrix, I could show it like this. Of course, this matrix is very much smaller than the actual matrix, but we just want to show an example. So this is what the image would look like in a matrix form. Okay, sorry, this is the one. This is the image in the matrix form. You can see that because it's a plus sign, all around it there is white, but in this cross mark there is black. So you can see here all the black pixels are having some value, but everything else around it is zero because zero would mean white. So this is our image representation in the form of a matrix. Now, suppose that you are given another image that contains a plus sign within it, but it's not as well defined as this plus sign. I mean, there are some blurry lines and all that, but it's a plus sign anyway. And you wanted your algorithm or your neural network or your CNN to be able to tell if both the images are similar or not. So to do that, you would have to create another matrix and to represent the other image that you have. So as you can notice, the values in this matrix are slightly different than this one, but the non-zero values are more or less in the same position. And we do have some extra values here because, like I said, the image is not very clear, does not have a very clear plus sign like this one. So there are some extra numbers over here, which is fine. But now when you multiply these two images, you will notice that you'll get a very large real number. You can see the multiplication here, taking product and sum. We know that in matrix, when we multiply, we take row into column. So whenever you're doing that, you'll be doing 0 into 0. Then all these three zeros will be zeros, but this 50 will get multiplied by 50. And every time all 50s are going to get multiplied, and you'll get a very large real number. So due to that, you can say that both the images are sort of matching because they have non-zero values in the exact same positions, which is causing you to actually get a very large real number upon multiplication. So that's the convolution layer. Let's now talk about the activation map. So the feature maps are summed with a bias term, and they are passed through a nonlinear activation function, which is known as ReLU, which is also called a rectified linear unit. So we've studied a couple of activation functions, and ReLU is one of those activation functions. So whatever maps that we created earlier, they are all passed through this activation function. And the purpose of this activation function is to introduce nonlinearity into our network because the images are made of different objects which are not linear to each other. So the images are highly nonlinear. Okay, so we are not talking about regression with a straight line. We're talking about nonlinear objects, and to introduce that, we would be requiring this activation function called ReLU, also known as um, the rectified linear unit. So this is why we require this kind of a function. Next, next step here is the max pooling step. So once the ReLU function comes to a pooling step in which the CNN downsamples the convolved feature to save on processing time while also reducing the size of the image. Okay. So basically, you're not going to keep the same sized matrix. You're going to try to reduce the size of your matrix so as to save time while processing your neural network, as well as to, to be able to perform a better analysis. And it would also help you to reduce overfitting. Okay, so we saw earlier in the previous videos that if you wanted to reduce overfitting, you might want to perform regularization, which might help in reducing overfitting, where you basically try to introduce noise in the inputs or try to remove some of the inputs. Okay, so same thing you could do here. Okay, and there are different types of poolings. We have max pooling, min pooling. In maximum pooling, we have a window that passes over an image according to a set stride value. And then at each step, it takes out the maximum value, which is pooled into an output matrix. And so it is known as a max pooling function. And if you had a min pooling function, instead of taking maximum value, you would take the minimum value. And then these values together would form a new matrix, which is known as a pooled feature map. Let's take a look at it. So as you can see, this is the very easy way you can see the portions being highlighted. So you have 7, 3, 8, 7. The maximum of these is 8. So 8 is the one that is pulled out. And here you have 5, 1, 5, 2, 1, 6. 6 is the maximum, so that's taken. Out of these four, 9 is maximum, so that is taken. And out of these four, 9 is maximum, so that is taken. So this is the output of the max pooling function. The next step in our neural network or CNN is flattening. So after multiple convolutional layers and downsampling operations, the 3D representation of the image is converted into a feature vector that is passed into a multi-layer perceptron to output probabilities. Okay, so this is a multi-layer perceptron, and we have studied this as well in our previous video. So once the downsampling is done and once you have created that simpler matrix, now you will convert your even that simpler matrix into a feature vector, which can be passed into a multi-layer perceptron so that it can work on different probabilities. So how do you convert a matrix into a vector? So the rows are concatenated to form a long feature vector. We'll see that in a minute. And if you have multiple input layers, then the rows are also concatenated to form an even longer feature vector. So this is what it looks like. If you, after doing max pooling, if you ended up getting a matrix of 9 different blocks, then flattening would mean just creating an array out of it. So you can see 1, 1, 0 right here, 1, 1, 0, 4, 2, 1, 4, 2, 1, 0, 2, 1, 0, 2, 1. So it's no longer a 2D array. It is instead a 1D array, which is created like this. Now, once you've done all this and you've passed everything into a multi-layer perceptron for probability estimation, next you have a fully connected layer. So the flattened feature map is then passed through a neural network And this particular step is made up of the input layer, the fully connected layer, which means a dense layer, and the output layer. And the fully connected layer is similar to the hidden layer in ANNs, but in this case, it's fully connected. And the output layer is where we get the predicted classes. So the information is passed through the network, and then the error prediction is calculated. And we all know the backpropagation algorithm, which we saw in the previous video. So then using the backpropagation algorithm, you can backpropagate the error and adjust the weights or other parameters to make your system work better. Here is a big diagram showing you everything about a CNN. So you see this is an image. These are the feature maps created. This is your convolution layer. These are the feature maps. Then you're going to apply the rectified linear unit plus max pooling function and create a pooled feature. So you can see these matrices are much smaller than the original ones. Next, you're going to take all these pooled features and create a flattened vector, which looks like this. And then this data is passed into a perceptron. And in that, you have a hidden layer. It's a neural network with a hidden layer that is a dense layer, which means it is fully connected. All neurons are connected with all other neurons in this portion. Okay. And finally, there's an output generated. And there's only one neuron in the output because we are performing classification where we just require a simple 0 or 1 to tell us which class it belongs to. So the final output is produced by the dense layer. It doesn't usually add up to 1, okay? It doesn't usually do that. But the outputs must be brought down to numbers that are between 0 and 1 because we want to show probability, right? So that is the role of the softmax function, which is another activation function. And the way this fully connected layer works is that it looks at the output of the previous layer, okay? And then it determines which features most correlate to a particular class. For example, if you had a program that is predicting that some image is an image of a dog, then it will have high values in the activation maps that represent high-level features like a paw or 4 legs or something. Okay. And similarly, if you had a program that had to predict some image of a bird, then it would have high values in the activation maps where there are features like wings of a bird or a beak or something. And this fully connected layer looks at what high-level features most strongly correlate to a particular class, and then has particular weights, so that when you compute the products between the weights and the previous layer, you're going to get the correct probabilities for all the different classes that you have in your output layer. So let's just quickly summarize what this looks like. So first of all, the pixels from the image are fed to the convolutional layer, which is going to perform the convolution operation, which we just saw about the plus sign, which would result in a convolved map. Okay, this map is then passed through the activation map, which is going to create a rectified feature map using the ReLU activation function. Then this image is processed with multiple convolutions and ReLU layers for locating the features. Then you're going to perform your max pooling, okay, to identify different parts of the image. This pooled feature map is again flattened to create one whole vector of one dimension. And then that's how your CNN is ready. Let's take a look at some applications of CNN. So it can be used for facial recognition. It can be used for handwriting analysis. You can also use it for personalized advertising, advertising based on people's interests. In driverless cars, for finding out signs on the road, what they mean. You could predict earthquakes and natural disasters, as well as human genome mapping. So that's it for this video. I'll see you in the next one. Thank you for watching.